Hello everyone, welcome to Vedantu JEE English. How are you? Hope everyone is good. If I'm audible and if I'm clear to you, please say clear. If I'm audible and if I'm visible, please say clear. Today is going to be the most high weightage chapter, you can say, whether it is going to be JEE mains or whether it is going to be JEE advanced. In both the in both the examinations, yes, it is going to have a lot of weightage, and people take these chapters to be scoring. So this is one thing which is going to be helpful for both the examinations. That's the reason why this is a very important class. So we will start it. Come on, please say clear. Please say clear. Yes, I remember you, Mr. Kachit Reddy. You have changed your name once I asked you to change your name. I said it is easy to what we call recognize people if with their names. So then you have changed your name. I remember you, man. I remember you. Just tell me if you can hear me, if you can see me. Please say clear. We will start. Please say clear. We will start. Come on. Super. Super. We'll start. Okay. So those who are going to be taking admission into 11th or 12th, if you have your younger brother or sister, all those people can give this examination, and there is going to be huge discounts if you are going to be performing well. So make sure you are going to be writing the MVSAT examination. Okay. So what are we going to do today? We are going to deal with photon theory. And then we are going to talk about radiation pressure to the next level, up to JEE advanced level. And whatever the things I am going to do in this class are not going to be there in any of the standard books, the ultimate formulas which I am going to give of radiation pressure. Because generally in the books you are going to find normal incidence, perfectly reflecting, perfectly absorbing. What if a fraction is going to get reflected? What if the incidence is going to be oblique? We will deal with everything. We will deal with every possible corner of radiation pressure. And then we are going to go to the very famous experiment called as photoelectric effect. Reason being, this is the experiment which proved or which established the particle nature of light. YDSC has established the wave nature of light, or interference has established the wave nature of light. In the same way, photoelectric effect has established strongly the particle nature of light. That's why these two experiments are very important. That's why you see in JEE Advanced, you'll have a lot of questions on YDSC. And in JEE Advanced, you'll see questions on photoelectric effect also, because these are two groundbreaking experiments. And then lastly, we are going to talk about D-Broglie's hypothesis. See, D-Broglie's hypothesis is very small, but almost whether it is JEE mains or JEE advanced, they are definitely going to mix the D-Broglie thingy with either Bohr's model, or they are going to mix it with photoelectric effect, or they are going to ask direct questions. If it is going to be direct questions, generally they are going to be asked in CET examination, right? Okay. Now, what is photon theory? See, light is taken to be made up of photons, and what are those things? The energy associated with these photons, the energy that is associated with these photons is given by h mu or hc by lambda, where mu is the frequency and lambda is the wavelength of that light or that electromagnetic radiation. Now you can clearly see over here, we are never talking about the intensity of light. So the energy of the photon we are talking about has nothing to do with the intensity of light. Just keep that in mind. Then how these photons are going to be moving, with what speed they are going to be moving? Yes, they move with speed of light. They move with speed of light in free space. They move with speed of light in free space. So if you are going to talk about what is the speed of a photon, it is same as that of the light. If it is free space, then it is going to be approximately 3 into 10 to the power 8. If it is some other medium, then you find out the speed of light in that. Even photons are going to be traveling with the same speed. Now, what about mass of these photons? Before we go and talk about these mass of the photons, you know this, or even if you don't know, this is something which has come from relativity. When a particle is going to be moving with certain velocity, its mass is going to be changing. So the mass of that particle or mass of the thingy which is moving with v speed is going to be given by this, where this m naught is the rest mass. M naught is the rest mass. Okay. I will be providing the PDF of this session. Don't worry. Then the rest mass can be written as what? M into under root of 1 minus v square by c square. I said that the photons are going to be moving with speed of light. So for photons, we can write v as what? C. In that situation, what is the rest mass of the photons? Rest mass of the photons is what? 0. Rest mass of the photons is 0. Okay, fine. Next. What about the momentum of these photons? How much momentum they carry? Okay, let us find that also. But before we go for that, generally in the books, momentum of photon will be given by h by lambda. Actually, it has come from one particular thing which is not there generally in all the books. Out of my interest, I started researching about these things and I found out one. Energy of the subatomic particles. Energy of subatomic particles is given by this relation, man. It's going to be p square into c square plus m naught square c to the power 4. If you already know it, it's fine. If you don't know, just have a rough idea about it. If you ask me whether you have to memorize this or not, no, you don't need to memorize it. Not needed. Okay, fine. What is P? P is the momentum of that subatomic particle we are talking about. M naught is the rest mass. So we found out that for photon, we found out that the rest mass of the photon is how much? 0. Then the energy of that photon can be written as what? P square into C square. And energy can be written as what? Hc by, oh, energy square, forgot. Energy square. Energy square is going to be P square C square plus M naught square C to the power 4. Then you are going to get is this C square is going to get kicked out. Then the momentum of the photon is going to come out to be what? H by lambda. So if you are going to say that, sir, do I need to memorize this? Not needed. What is important? Momentum of photon. You need to know how momentum of photon has come out to be h by lambda, and I have given you. I have given you how the momentum of the photon is going to be h by lambda. Now, if we talk about photons, generally we are going to be talking about those sources which are going to be emitting some amount of energy, and whatever the energy they are going to be emitting, it will be in the form of photons is what we say. Whatever the radiation that is going to be coming out, like for example, we have a bulb. Let us take this to be the bulb. What the bulb does, bulb is going to be emitting light, right? So basically what the particles or that light is going to have, photons. So basically it is sending photons in all the directions, right? Now, obviously this bulb, whatever I am talking about, is going to have some power. What is that power? Power is represented with P. Don't get confused with the previous one. Okay, this we will we'll do one thing. We'll just keep it as power. Unnecessarily you'll get confused with the momentum. So power, what is power? The rate at which energy is going to be emitted. So power can be written as the rate at which energy is going to be emitted per unit, time. How much energy is going to be coming out means it depends on the number of photons. So let's say some capital N number of photons have come out, and energy of each photon is hc by lambda divided by time. So that hc by lambda, I will write this one as E. I will represent this with E. So now you tell me the number of photons that are going to be emitted per unit time by this bulb is going to be the power of that bulb divided by energy, where what is this energy? It is the energy of each photon. So if they have given that there is a bulb, if they have given the power, if they give what is the wavelength of the light that is emitted, then you can easily calculate energy of photon. That power of the bulb divided by energy of each photon gives you the number of photons coming out per second. Number of photons coming out per second can be easily found like this. Okay, fine. Then, sir, are we always going to get power? Are they always going to give an information about power? Or are they going to give something else? Sometimes they are going to give information about something called as intensity. Sometimes they are going to give information about something called as intensity. So what is this intensity? Represented with I. Intensity represented with I. So what is this? It's the energy crossing per unit time normal to the area. Intensity is energy crossing per unit time normal to the area. So I can write I as the energy by time divided by the area. Can I write like this? Yes. So how much energy has come out? The amount of energy that has come out is going to depend on what? The number of photons that have come out into energy of each photon. Let's say if we have some 100 photons coming out, 100 into energy of each photon gives you the energy that has come out, right? So I can write I as what? I can write I as number of photons into energy of each photon by time times the area. So if you are ever in need of how many photons are coming out per unit time from a source, then if they have given information about I and A, then this is the thing you have to use. Never ever forget, A is what? The perpendicular area to the energy flow. Never ever forget that. Because this is going to be the most important thing whenever I'm going to do oblique incidence for radiation pressure. Okay. So, sir, 1 second. I would like to just add one more page. Oh, shit. What happened? I have to change the background of this. I thought it will come out to be okay, it's green. Fine. Just 1 second. If I can see. Okay, leave it. Leave it. I thought the same black is going to get added. Uh-oh. What happened? What did I do? Just a second, man. I think I have opened something else. Oh shit. Just a second. Okay. Something happened. Fine. Now look, what if the energy was not going in one particular direction, or oh, I missed it. Just a second. Look, my intention is, if this is how the energy is flowing, and if they have given this as the intensity, then if the area I am talking about is like this, here you can clearly see that the area is perpendicular, right? Here you can clearly see that the area is perpendicular. So in this situation, I can say the number of photons that are going to be reaching per unit time onto this area is going to be I into A divided by E, where E is energy of each photon. But it is not mandatory every time. It is not mandatory that whatever the area we are going to take should always be perpendicular. For example, if the area was like this, if the area we have taken is like this, let us take this area to be some A1. Then how many photons will be striking this? The number of photons that are going to be striking this one, the same number of photons will be striking this also, because that much of light is blocked. So if I am going to talk about this to be theta, then this A1, when projected perpendicular to the flow, it will come out to be what? A1 cos theta. So this is what you have to take as A, and the number of photons that will be striking the green one, the same photons will go and strike the red one. So now how many photons are going to be striking this green one? Means it is going to be I, the perpendicular area is A, divided by E, which is going to be I times A1 cos theta divided by E. So always keep in mind, if the area they have given is not perpendicular to the direction of flow of energy, you take the projection of that area perpendicular to the flow, only then you are going to get the number of photons. So when it was defined, the intensity was defined, it was the energy crossing per unit time perpendicular to the area. Never ever miss that. Never ever miss that. Okay. Let's see to what extent you will be able to use now. Come on. Do this. The intensity of sunlight on the surface of Earth is 1400 watt per meter square. And now, assuming the mean wavelength of the sunlight to be 6000 angstrom, what did they give? They have given it to be 6000 angstrom. Now, calculate the photon flux arriving at 1 meter square area on Earth perpendicular to the light radiation. So, photon flux is nothing but how many photons are coming per unit time. That's what they are asking us to find. But before we go for that, we need to find out what's the energy. How much energy the photon is going to have is what we have to find out first. So the energy the photon is going to have is hc by lambda. H is Planck's constant, which can be written as 6.626 into 10 to the power minus 34 into the C value, which is 3 into 10 to the power 8 by the wavelength, which is going to be how much? 6000 angstrom, which is going to be 10 to the power minus 10. From here, you are going to get energy of each photon. Now, if you want the number of photons, anyway, they clearly mentioned perpendicular. That means it is striking normal to the area. Then the number of photons that are going to be coming is going to be I into A divided by E. How much is the I value? It is 1400. What is the area they are talking about? It is 1 meter square divided by what is the energy? So you have the energy above. Just put that, do the calculation, you are going to get how many photons are going to be striking 1 meter square area. How many photons are going to be striking 1 meter square area. Next, the number of photons emitted from the sun per second, assuming the average radius of Earth's orbit to be 1.49 into 10 to the power 11. Okay, look, somewhere over here, let's say we have sun, and on this we have Earth somewhere over here. When compared with sun, the size of Earth is going to be very small, and Earth is orbiting this. And the radius, when we talk about, let us take the radius to be some r, that is the orbiting radius, Earth orbiting the sun. Now let us go back, let us look at the data, the number of photons emitted from the sun per second. Now they are not talking about how much is going to be reaching Earth, they are talking about how many are emitted from the sun. Let us take the power of the sun. Obviously, sun is going to be giving away energy, right? So the energy it is going to give per unit time is power. So whatever the energy this is giving is going to go in all the directions, right? It goes in all the directions. It is going to go in all the directions, and it is going to be symmetrical, because you can treat it a kind of a sphere is going to be obviously symmetrical to all the points which are going to be around it. So this is how the energy is being given out. That is how the photons are going to go in all the directions. Now, if I have to calculate how many photons are coming from sun, number of photons that are going to be coming from sun, number of photons per unit time that are going to come from the sun, already I have explained, is going to be the power of the sun divided by what? Energy of each photon. But did they give information about power of the sun? No. But what did they give? They have given information about how much is the intensity at this location. So Earth is part of this big sphere. So whatever the power is given by the sun is falling on this sphere, right? Onto how much area it is falling? It is falling onto 4 pi r square. So if you remember the definition of intensity, it is going to be the energy per unit area per unit time. Energy per unit time can be written as power. So intensity can be written as what? The power that is going to be present per unit area. So how do I get the power that is going to be given by the sun? Intensity multiplied with the area on which that power is spread or that energy is spread. What is the area on which this energy is going to go and fall? It is going to be falling on 4 pi r square area. So it is going to be I into 4 pi r square. It's going to be I into 4 pi r square. Okay. Now we got the power. Just keep it over here. Then we are going to get number of photons that are going to be emitted from the sun per unit time. Number of photons emitted from the sun per unit time. Intensity is given. How much is the intensity? The intensity is given as 1400. So all you have to do is you put I as 1400 and then 4 pi. What is the average radius of the orbit that the Earth is going to be taking around Sun? It is 1.49 into 10 to the power 11. So you put 1.49 into 10 to the power 11 square. This much calculation you have to do. Then as I said, once you get this, put the power over here. We already calculated the energy of the photon. Then you get the number of photons that are going to be coming out from the surface of sun. Generally, when these kind of questions are going to come, the calculation part is going to be slightly difficult. So in JEE mains, if they are going to ask questions on photon flux or number of photons coming out per unit time, my suggestion to you is that if it is a numerical question, attempt it. No, sorry. If it is a numerical question, you leave it. If it is a MCQ question, you do it. Why? You can calculate the rough values and then you can match the option. If it is a numerical one, doing the exact calculations in examination is going to consume a lot of time. So my suggestion to you is that you better leave these kind of questions if they are going to be asked in numericals. Okay. Now, let us talk about radiation pressure. First, what I'll talk about is normal incidence. Like every book, I will also talk about normal incidence. Like every book, I will also talk about normal incidence. Okay. Right now, whatever the surface I am going to be taking, I'll just take that it is a perfect reflecting one. It's a perfect reflecting surface. Okay, fine. Now, let us take that the area we are talking about is this. The area we are talking about is this. And let us take, we have a photon which is going to be coming towards this wall. One photon. Let's take one photon at a time. What will be its momentum? H by lambda. Momentum of photon is h by lambda. Now after the collision, as it is going to get reflected back, because I said it is a perfect reflecting surface, after the collision, what will be the momentum of the photon? The momentum of the photon is going to be h by lambda and it is going to be to the left side. Okay, fine. Now, can you tell me what is the change in momentum? I want change in momentum. Momentum is a vector. It has direction. So if I am going to talk about the initial momentum is h by lambda. I am just taking this direction to be I cap. And what is the final momentum? The final momentum is h by lambda in the minus I cap direction. Right? Okay. Now, what is the change in momentum of the photon? The change in momentum of the photon is obviously final momentum minus initial momentum. So you are going to get minus 2h by lambda I cap. This is just for one photon, but when we throw light onto this area, will only one photon strike the area? No. There will be many photons, right? So let us take that some capital N by T number of photons are going to strike per unit time. Okay. So if I am going to take capital N by T photons strike per unit time. Okay. These many photons are striking per unit time. Then all those photons are going to be experiencing the change in momentum. And one thing which you have to keep in mind is that what is the force that this is going to experience is going to be the change in momentum by time. So like that, if you want to talk about the total force on all the photons, then all the photons into delta P by T. So if I want to talk about the total force acting on the photons by the wall, can I simply say N by T photons are going to strike every second and their momentum is going to change by this much, which is going to be minus 2h by lambda I cap. This is the force that is acting on photons. For every action, there will be equal and opposite reaction or not. So if the photons are experiencing a force to the left side, then the wall will experience a force to the right side or not. So what will be the force on the wall? So can I say the force on the wall is going to be exactly opposite, which is going to be N by T into 2h by lambda I cap. And what is N by T, man? The number of photons striking per unit time. So if the intensity of beam is given to us, let's say we have a beam of light, and if the intensity of it is given, then do we know how many photons are going to be striking this particular area? Yes, just now we discussed that. The number of photons which are going to be there per unit time is going to be I into A divided by E, where E is energy of the photon. Now, if I want to talk about force on the wall, I can write N by T. 1 second, let us go back. Just see what is here. N by T. See there, N by T into 2h by lambda. So N by T can be written as what? Intensity A by E, where E is energy of the photon, which is going to be hc by lambda, into what? 2h by lambda I cap. So h by lambda are going to get cancelled out. So the force that is going to be acting on the wall is 2I by C into the area. So if that area I am going to take it to the left side, then the force on the wall acting per unit area on the wall will become the pressure or not. And that pressure is because of what? Who is creating that pressure? That pressure is created because of the photons or the radiation that is sent onto the wall. The radiation that is sent onto the wall, right? That's why whatever the pressure is going to get created, we call it as radiation pressure. The force acting on the wall per unit area can be called as what? Pressure, but I'll call it as radiation pressure. So in the case of, what happened? Two I by C. If it is a perfect reflecting surface, then it is 2I by C. What if it is a perfect absorbing surface? What if it is a perfect absorbing surface? I don't need to do too much for perfect absorbing surface. I can explain it over here itself, because we can compare the perfect reflecting one with perfect absorbing one. Look, we have photon of momentum h by lambda. It goes, it strikes, but it is not going to get reflected, because we are talking about a perfect absorbing surface. We are talking about a perfect absorbing surface. So in that case, after striking, the photon will come to rest, because it is absorbed by the wall. So in this situation, what is the change in momentum? See, if I am going to talk about change in momentum, it is final momentum minus the initial momentum. Final momentum is 0, initial momentum is h by lambda I cap. So if you compare the previous situation, where we had minus 2h by lambda I cap, now we have only minus h by lambda I cap. That means I can clearly see that the factor 2 is missing. As the factor 2 is missing, I can say that directly without calculation, I can say that the radiation pressure in this case, in the case of pure absorption, the radiation pressure in this case can be written as what? Simply I by C. The 2 factor will be missing. These are the 2 important things which are going to be given in almost every book. In almost every book they give this. But this is not what I am interested in. Why? There are multiple conditions which we have taken. We have taken normal incidence. For your kind information, let us go back. Normal incidence is given. And we are talking about a perfect reflecting one or a perfect absorbing one. A perfect reflecting or perfect absorbing. Is it mandatory that always they have to give perfect reflecting and perfect absorbing all the time? No. When we talk about reality, when we throw light onto something, a portion of it gets absorbed, a portion of it is going to get reflected. So what if X portion gets reflected? What if X portion gets reflected? Not everything. X fraction. It's better to write X fraction. What if X fraction gets reflected? In that situation, what will happen? You only just think. Only X fraction is getting reflected. That means 1 minus X fraction of light is going to get absorbed. So 1 minus X portion is going to have change in momentum as h by lambda. And X fraction is going to have momentum change as minus 2h by lambda. For your kind information, you only see. When the photon is coming back, you have minus 2h by lambda. And when the photon is absorbed, you have the change in momentum as minus h by lambda. So if I am going to talk about only X fraction to be getting reflected, I can talk about the total momentum change to be what? X fraction is getting reflected, right? So the change in momentum in that X fraction is going to be what? Minus 2h by lambda I cap into X plus 1 minus X into minus h by lambda I cap. because that's the portion which got absorbed. So from here, what are you going to get? From here, what are you going to get? You only just see. This is how the momentum we have got. And ultimately, when you do the calculations, I'm skipping because we can't just keep on doing the calculation. So the radiation pressure ultimately comes out to be 1 plus x into I by C. So if it is perfect absorbing, if it is a perfect absorbing one, then nothing is getting reflected. The fraction that got reflected is going to be how much? 0. So in that situation, you get the pressure, the radiation pressure to be how much? I by C. If it is a perfect reflecting one, then what will happen? If it is perfect reflecting, the fraction which got reflected is 1. Like everything got reflected, 100% got reflected. Then the radiation pressure is going to be 2I by C. Never ever forget. So my suggestion to you is that you better memorize this rather than memorizing radiation pressure for perfect absorbing situation to be I by C and radiation pressure for perfect reflecting situation to be 2I by C. Better you memorize this. And if it is going to be JEE advanced, they won't talk about normal incidence. What if it's not normal incidence? What if it is not normal incidence? What if it is going to be an oblique incidence? What I mean to say, for example, we have a wall like this and we have the beam striking like this. So isn't it oblique? Yes. So do we have an angle over here? Yes, we have an angle. So let us talk about what is happening for one particular photon, and that too, not to complicate stuff, let me talk about pure reflecting one, perfect reflecting one. I'll get it for perfect reflecting. Then instead of that perfect reflecting, I'll talk about perfect absorbing also. I'll talk about a non-perfect reflecting nor absorbing one. In reality, we are not going to have everything which is going to be perfectly absorbing or perfectly reflecting. Partial reflection is going to take place. So now let us see a photon which is going to strike like this. What it does, it comes and then it is going to be making a collision and then it is going to be bouncing off, as it is a perfect reflecting one, and photons are going to make perfect elastic collisions if they are going to bounce off like this with the wall. Let us say if the angle of incidence is going to be theta, then the angle of reflection will also be what? Theta. And what is the momentum of this one? H by lambda. After striking, the momentum of this one will also be what? H by lambda. Now, can you resolve that into components? Yes. I can resolve into two components like this. If this angle is theta, then this angle is theta. So in this direction, I have H by lambda cos theta. And in this direction, we have H by lambda sin theta. Now, we can do the same thing with this one also. What is this angle? This angle will be theta. Then I can say in this direction, H by lambda cos theta is there. And in this direction, H by lambda sin theta is there. So let me write what is the initial momentum and what is the final momentum. So what is the initial momentum? Write it in the vector form. If you write it in the vector form, h by lambda cos theta I cap, and down we have h by lambda sine theta minus j cap. What is the final momentum? The final momentum is minus h by lambda cos theta I cap, and down h by lambda sine theta minus j cap. Okay, fine. Now let us talk about what is the change in momentum that particular photon has suffered. This minus this, which is going to give you what? Minus 2h by lambda cos theta. Now people are going to be like, sir, when it was normal incidence, we got the change in momentum to be 2h by lambda, right? Now we got 2h by lambda cos theta. That means you are going to say that there is a cos theta factor which is extra over here. So when we have 2h by lambda, we got the pressure to be 2I by C. When it is 2h by lambda, we got the pressure to be 2I by C. As the momentum now is 2h by lambda cos theta, so can I claim that the pressure is going to be 2I by C cos theta? That's where majority of the people are going to be committing a mistake. No man, because there will be one more cos theta which is going to come up. Why? Let us look. This area is not perpendicular to the beamed. So whatever the area we are talking about, this area, whatever is there, this area is not perpendicular to the beam. Let us take that area to be some A1. What we have to find out, we have to talk about an area which is going to be perpendicular to the beam. Projection of A1. What will be this angle? It will be theta. If you want, you just check. I have taken normal, right? If I am going to be making this one perpendicular to the beam, then you have to rotate it by some angle theta. So what is this area? It is A1 cos theta. So how many ever photons will be reaching this area, those many photons will go and strike this vertical area. So how many are going to be reaching this area? The number of photons that are going to be reaching that area is going to be I into the perpendicular area divided by E. So if I am going to talk about the total change in momentum of the photons, whichever are going to be striking, is going to be n by t into minus 2h by lambda cos theta I cap. And for your kind information, that n by t should be written like this. As a result, the total change in the momentum of the photons is going to be, you only see n by t is this, IA1 cos theta by E. IA1 cos theta by E, which is HC by lambda, is going to be minus 2h by lambda cos theta I cap. Obviously, let's go back. So I have multiplied with number of photons striking per unit time, then this is also going to become per unit time only. This is change in momentum. Now total change in momentum, if I am going to talk about per unit time, I have to put time, then I'll get n by t on both the sides. My bad, I should have written it long back, by time. So this is going to give you force on photons. This is going to give you force on photons. And if you are going to look at, you are going to get 2I by C cos square theta I cap into A1. Now force on wall. Then the force on wall is going to be what? 2I by C cos square theta I cap times A1. Then the force on the wall that is going to be acting per unit area is going to be 2I by C cos square theta. So I can say the radiation pressure in this case is not depending on cos theta, it is depending on cos square theta. This is something which they haven't touched till date. This is something which they haven't touched till date. Yes, you can expect questions on this one. You can expect questions on this one. This part hasn't been explored till date. Okay. Now, is it mandatory that always it should be a perfect reflecting one? No. So what if a fraction gets reflected? What if x fraction of light gets reflected, not 100%. 100% means x is 1. 100% means you have to take x as 1. Okay, fine. Now let us go back. We have 2I by C, right? I am directly giving you to save time because there is no point in keep on solving this. So the radiation pressure in this case will come out to be 1 plus x into I by C cos square theta. Now some people are going to get into trouble in choosing the x value. X is the fraction of light, right? For example, what should be taken as x is something which is going to be bothering many people. For example, if they say 25% gets reflected, that means 25 by 100 fraction is getting reflected. That means 1/4 of the fraction is going to get reflected. That means our x is this much. If someone says 75% gets reflected, if someone says 75% got reflected, then 75 by 100 fraction got reflected, which is going to be how much? 3 by 5. So you should take your x as 75 by 100 is 3 by 4, which you can take as your x. So my suggestion to you is that instead of mugging up 2I by C or I by C, you mug up this one. You mug up 1 plus x into I by C cos square theta. It will help you save lot of calculations if there is any complicated question coming up. Because you can't keep doing this derivation in the examination. And one more thing, anyway you are going to be mugging up 2I by C, I by C and all that stuff. So instead of mugging up 2I by C, instead of mugging up I by C, you memorize this one. In the examination, if oblique incidence is going to come, there is high possibility that majority of the people won't get the answer, but you will get them. Okay, fine. Take a question which is a previous year's question. This is a previous year's question. I don't remember, I think 2019 or 2020. 2020 question. 50 watt per meter square energy density of sunlight is normally incident on the surface of a solar panel. Look, highlight the important things. Always keep in mind, we have to see how it is incident. It is incident normally. It is incident normally on the surface of a solar panel. Some part of the incident energy, 25%, is reflected from the surface and rest of it is absorbed. So what is the x fraction? What is the x fraction? 25%, right? Sometimes to trick you, they will say 25% is absorbed. So you have to be careful. Here they clearly mentioned 25% is reflected. So the x we are talking about is 1 by 4, man. The x we are talking about is 1 by 4. Clear. Now, if I am going to talk about any of the radiation pressure, the radiation pressure is going to be 1 plus x into I by c cos square theta. For your kind information, theta is going to be 0 in this case because we are talking about normal incidence. For normal incidence, angle of incidence will be 0. So I am going to get 1 plus 1 by 4 into I by c as the pressure, which is going to be 5I by 4c. Okay, I got the pressure, but they are not talking about pressure, they are talking about force. They are talking about force. And one more thing, did they give the intensity? Yes, they have given the intensity. What is that? 50 watt per meter square. 50 watt per meter square. Now you tell me, what are you going to get? If you want the force, force is going to be what? The pressure which is there multiplied with the area. And what is the area, man? What is the area? They gave it to be 1 meter square, right? Okay. So pressure is 5 I by 4c into what is the area? 1 meter square. So 5. What is the I value given? I value given is 50. Divided by 4 into 3 into 10 to the power 8. So you are going to have 250 by 12 into 10 to the power minus 8. Now you look at the options. This one, they are asking you to go for the close value. So 250 by 12 will be around 20. So what will be your answer? This. So if you have known this, look at how easily we are able to calculate. If you don't know this one, you have to start from the scratch. Neither it is perfectly reflecting nor perfectly absorbing. So you are going to get stuck in the examination. You are going to get stuck in the examination. So that's why my suggestion to you is you mug up this. And till date, they haven't bothered about oblique incidence. If there is oblique incidence, then this formula will save you in examination. This is going to be the mother of everything, whatever we have learned till now. If you put x as 1, if you put theta as 0, you get 2I by c. If you put x as 0 and if you put theta as 0, you get I by c. So perfect reflecting, perfect absorbing are covered. That's why make sure you memorize this. Okay. Now, I would like to give some homework question, but this question which I am going to give as homework is on advanced level, man. Is on advanced level. What is it? We have a sphere like this. We have a sphere like this, and we have a light, or you can say a parallel beam of intensity I is going to be thrown onto this one. And if I am going to talk about the radius of this one, I am just taking it to be capital R. And I would like to give few more observations or information about this particular thing. It's a perfect reflecting one. This one is a perfect reflecting surface. It's a perfect reflecting surface. It's a perfect reflecting surface. What I want is, see, this radiation, that means these photons, they go and strike this sphere, right? And when they strike, obviously they are going to be changing their momentum or not, because they get reflected. When there is change in momentum, there will be force on the photons. Then photons are also applying force on the sphere, action reaction. What I want is find Find force on this sphere. Find force on this sphere. I'll give you the answer also. You can verify that whether you will get the answer or not. You get it to be I by C into pi r square. Yes, there is integration involved in this. That's why I said this is JEE advanced level 1. There is integration involved in this. That's why I clearly said it is an advanced level 1 and you have to take ring elements to get the answer. You have to take ring elements to get the answer. Keep that in mind. Okay. With this, we are done with photon theory. With this, we are done with photon theory. Now we know everything about what are photons, with how much speed they are going to move, how much momentum they have, right? When they are going to be undergoing reflection, when they are going to be undergoing absorption, when they are partially reflected, partially absorbed, what they are going to do to the surface. And one more thing, you should get a doubt. Sir, when I am there inside the classroom and when I go and stand in the sunlight, in both the situations, I don't feel much of a difference. I don't feel much of force acting on my body. Why is that? If I am there in the classroom, the number of photons striking me are less. If I go and stand outside in sunlight, there are more photons striking me. As there are more photons striking me, then more photons are changing their momentum, so there is more force on my body. Why am I not experiencing more force when I go out there in the sunlight? Look, already your body is under atmospheric pressure. 10 to the power 5 Newton per meter square is acting. And if you talk about radiation pressure, radiation pressure has c in the denominator, speed of light in the denominator. That means radiation pressure will be in the order of 10 to the power minus 6, minus 7 like that. You are experiencing 10 to the power 5 due to atmosphere. And radiation is applying 10 to the power minus 6 order. Will it make much of a difference whether it is added or not? No. So that's the reason why when we go and stand out in the sunlight, as there are more photons striking me, for sure there is more force acting on me, but that more force whatever is there due to the photons, it is very small in amount when compared with the atmospheric pressure. So we won't feel whether that force is acting on us or not. Then why are we learning it, sir? If it is not going to be contributing much, then why are we learning it? I'll give you one small example. When you are there in your childhood, let's say when you are 5 years old, if you observe yourself in a mirror 7 days, consecutively 7 days, do you feel any difference in your height? No. But if you are going to look at yourself in the mirror after some, let's say 7 years, then definitely you will see some difference in your height, right? So the changes in your body were very, very, very small. So these small quantities over a big period of time will create a difference. So when scientists are going to be sending satellites or something into the space stations, they are not going to be like this, that they are going to be staying there for 1 minute or 1 hour or 1 day or 2 days. They are going to stay there for years. So continuously light from sun is going to be striking them. Although it's a small amount of force, over 20 years or 30 years, it can contribute for a big change. So if we are going to talk about physics and when we are going to be taking satellites into the orbits, yes, we have to take into consideration the radiation pressure also. If you don't take into consideration, yes, definitely we are going to fail. Okay. Now, let's go to a very important part, which is photoelectric effect. Let's go for photoelectric effect. Why is this experiment so important? This experiment is very important because this is the one which has clearly established the particle nature of light. So what the particle theory says and what the wave theory says, we will clearly talk about them. So first of all, let's see what is photoelectric effect. The phenomena of emission of electrons from the surface of certain substances when suitable radiations of certain frequency or wavelength are incident upon is called as photoelectric effect. What happens in photoelectric effect is clearly mentioned over here. Simple words, you throw some light, some electrons are going to come out from that metal plate. That's called as photoelectric effect. Now we will try to understand photoelectric effect in terms of wave theory, in terms of photon theory. Wave theory and photon theory. In both the ways, we'll try to understand why the electrons are coming out. Okay. So what the wave theory says, you can treat radiation as an electromagnetic wave, and every one of you know that in electromagnetic wave there will be electric field oscillating. In electromagnetic wave there will be electric field oscillating. So what that electric field is going to do is, that electric field is going to be applying force on the electron inside the metal surface. The electrons which are very loosely bound, those electrons are going to be easily disturbed by anything, whether it is electric field, right, or whether it is going to be photons. No matter what you are going to talk about, if you talk about the loosely bound electrons, they can be easily moved around or they can be easily taken out because they are loosely bound. Now these electrons, when they come in interaction with the light wave, the electric field in the wave will make the electron oscillate, and that electric field keep on oscillating. It will keep on increasing the amplitude of oscillation of the electron. At one point of time, the amplitude of oscillation of the electron becomes so big that it breaks the bonds with the atom and it just goes out. And that's what we see as photoelectron emission. When we throw light, we get electrons out. Wave theory says that there is electric field, slowly the electron will be made to oscillate, and slowly the amplitude of that electron is going to be increased, and at one point of time the electron gains enough energy to go out. So this whole process takes some time. What? The light goes, strikes, and then the electric field makes it oscillate, and the electron should gain sufficient energy, then it is going to go out. So according to wave theory, light takes some time to emit the electron. That's what the wave theory says. And one more thing is that, you know from electromagnetic waves that more is the intensity of light, more is the amplitude of electric field. So more the intensity, more the electric field. More the electric field, then the electric field can make the electron oscillate even faster. So higher the intensity, higher the electric field, higher the energy given to the electron. Keep in mind, if the intensity of the light is very small, then the electric field of that light is very small, then the force applied on the electron will be very small, and the electron will move slowly, but it will be oscillating. So might be after 1 year or 2 years, it will gain enough energy, then it comes out. So wave theory says that irrespective of what frequency of light you throw, irrespective of what frequency of light you throw, as long as you are throwing light, that light will have electric field. If the intensity of that light is small, then the electric field will be small, then the oscillations given to the electron will be small. So it will take more time to come out, but definitely it will come out. So now we have seen two important things. First important thing is that electron takes some amount of time to come out. Second important thing is that no matter whatever the light you throw onto the metal surface, irrespective of how much energy it is going to have, even if it is going to be a small energy one also, the electron will be able to come out, but it will take more time. It will take more time. It has nothing to do with the frequency. Now what the photon theory says, photon theory is like, you visualize like this, you visualize like this. To make you understand, I have taken an analogy. This plastic ball, whatever is there, you treat it as photon. And this bottle, whatever is there, you treat it as the electron. And one electron will interact with one photon at a time. Just keep that in mind. Now look, this plastic ball, when I throw it onto this bottle, there will be two possibilities. That plastic ball will knock out this water bottle, or the water bottle will be as it is. The plastic ball is not able to knock the bottle out, right? So if the energy of the plastic ball is very small, if I throw it with small kinetic energy, then will the bottle fall? No. So whenever I am going to say whether the bottle is going to fall or not, if the bottle falls, electron comes out. So you relate like this. How you relate? If the bottle falls, you can take that electron comes out. So if the bottle is not able to fall, then the electron will not be coming out, because the energy of the plastic ball is not enough, or the energy of the photon is not enough to make the electron come out. Think in that way. Now you visualize, if I throw the plastic ball very slowly onto the bottle, will the bottle fall? No. If I throw the plastic ball hard, then there is a possibility that the bottle might fall. And one more thing, how much time the bottle takes to fall? If this one has enough energy, the bottle will fall immediately, right? It is not going to be like, once the plastic ball strikes, the bottle is going to be like, okay, dude, I'm going to fall, but I'll fall after 1 year. It doesn't happen like that. So the plastic ball, if it has enough energy, definitely it will knock out the bottle immediately. So photon theory says that two important things. The first important thing is that if the bottle falls, it will fall immediately. That means if the electron comes out, it will come out immediately. If the electron is going to be coming out, it will come immediately. Second thing is that there should be certain minimum energy for this photon, only then the bottle will fall. As I said, if you throw this plastic ball slowly onto the bottle, will the bottle fall? Never. You can try it for your entire lifetime. You throw with small energy, this plastic ball, you throw it with small energy, then the bottle is never going to fall. So photon theory is saying that minimum energy is needed for the electron to come out. Electron coming out is nothing but bottle has to fall off. So on the basis of photon theory, according to the photon theory of light, light consists of particles. All of that is not needed. When the photons are incident on the metal surface, they collide with the electrons. In some of the collisions, a photon is absorbed by an electron, thus the electron gets energy. If this energy is greater than the binding energy of the electron, it comes out of the metal surface, and the extra energy given to the electron becomes its kinetic energy. Clearly you can visualize. If you throw it very fast, then the bottle falls with some kinetic energy. You only visualize. If you are going to throw it slow, the bottle won't fall. If you throw it very fast, then the bottle flies off. So, as I said, you think of the bottle as electron. So the electron flies off. That means electron will become free and it will also have kinetic energy. Now look, these are the two theories. We have to do the experiment also, na? Let's see what the experimental results are saying. Wave theory says that electron should come out after some time. Photon theory says that if there is electron emission, pakka it should come out immediately. Wave theory says that irrespective of energy of the light, irrespective of frequency of the light, if there is energy sent onto the metal plate, pakka electron will come out. And what the photon theory is saying, minimum energy photon is needed. That means there is certain minimum frequency, because energy of photon is h mu. So there is certain minimum frequency, only then the electron will come out. So who will be proved right, who will be proved wrong? Let's see what the experiments are going to say. So in order to do that experiment, what we are going to do is, we have a plate here. This is called as cathode plate, or you can call it as emitter. And this is the anode plate. Light is going to be thrown onto this cathode plate, and then we get electrons from this one. And these electrons are going to be made to go through the, or go towards the anode, or sometimes we are going to decelerate. So sometimes what we are going to do, we are going to be applying electric field. Is that visible? Yes. Electric field like this. So in this situation, force on these electrons will be what? Backwards. So we are discouraging the electrons to go to the anode. So in order to do that, this should be at higher potential and this should be at lower potential. So I have to tap it in such a way that this will be at higher potential and this will be at lower potential. Look, if I do the tapping here, right? So you can see, yes. So if the tapping is done over here, that is left extreme, then the anode is at lower potential and the cathode is at higher potential. As a result, you will have electric field in this direction. And the electrons are discouraged because the force on those electrons are to the left side. So when I am doing the experiment, sometimes I need to encourage the electrons also. So when I need to encourage the electrons, then I can do the tapping here. Like this is the extreme encouragement I can give. So now if you see, this is at higher potential, right? This is at lower potential. As a result, you will have the electric field like this now, and these electrons experience a force opposite to the electric field, and we are going to make them accelerate. So what I want you people to understand is that once the light is going to be emitting the electrons, I can make them accelerate, I can make them decelerate. I can make them accelerate, I can make them decelerate by adjusting this tapping point. This tapping point, whatever we are talking about, depending on where we tap, we can change the potential difference. Sometimes I can maintain this at higher potential, this at lower potential, this at lower potential, this at higher potential. Okay. Now the whole setup is clearly understood to you. And one more thing, photoelectric effect is very important for JEE mains as well as JEE advanced. You should have proper understanding of these things. Otherwise, you will struggle. And I have great depth knowledge of this photoelectric effect. And trust me, even the books haven't not mentioned properly. I struggled a lot and gathered the data and finally realized what are the exact things they are talking about. So don't miss on to this session. Okay, fine. Overall, we have a rough idea. Light will emit the electrons. After the electrons are emitted, by controlling this circuit, I can make them accelerate, I can make them decelerate. Okay, fine. Now I want to talk about photocurrent versus intensity. I would like to give one very important point which is not there in the books, which is not mentioned in the books. I realized it by spending lot of time on reading through different what we call articles and all those things. Look, man, whenever they are going to say intensity, intensity in photoelectric effect, if they don't mention If they simply say intensity, and if you are talking about photoelectric effect, they are not talking about the intensity what we have learned, that is watt per meter square. They are talking about number intensity. What is number intensity? Number intensity is number of photons striking per unit time. So number intensity of photons is different and the watt intensity is different. What we have seen like some time back, 50 watt per meter square. 50 watt per meter square is watt intensity. And in photoelectric effect, every time when we are going to talk about intensity, keep in mind it is number intensity. So if they say intensity is increased, number intensity is increased. That means if you are sending 100 photons, now you are sending 200 photons. If you are sending 300, and if you say intensity of the light is increased, then instead of sending 300, now you are sending 600. So that is what is the intensity whenever we are talking about photoelectric effect. So whenever I write the word intensity, everywhere in photoelectric effect, it is number intensity, not watt intensity. This is something missing in every book. They won't talk about it. Okay, fine. Now look. So what will be the photocurrent and the relation between the intensity? So better I will directly write it as number intensity. Although the books is going to show you intensity, and this is photocurrent. Now you might have a doubt, sir, what is photocurrent, sir? I don't get it. You haven't explained it. What is photocurrent? The board is quite bright. Okay. Think it is manageable, man. Just check once. Okay. As this is white slide, na? That's why you are finding it a bit difficult. Black slide, when it is going to come, it is going to be fine. Look, man, when the electrons are going to go here, and the electrons are going to travel all the way, because we have a circuital diagram. So when the electrons are able to reach from here to here, the circuit is complete. If the circuit is going to be complete, then current is going to flow or not. And the circuit is complete because of what? The electrons which have come because of photons which have struck the metal plate and made the electrons come out. So when light strikes the plate, electrons come out. So those electrons which have come out because of the light, we call them as photoelectrons. And those photoelectrons travel to the anode, and then they complete the loop, they complete the circuit. As a result, whatever the ammeter is going to be connected over here will detect some current. And as the current in the ammeter is because of throwing light onto the cathode, that's why we call that particular current as photocurrent, because photons are responsible for the current flow in the circuit. So now look, when I throw, let's say, for example, when I throw 100 photons, let's say 1 electron is coming out. Then if I increase the intensity and if I send 200 photons, then 2 electrons will come out. 300 photons, 3 electrons will come out. So as I increase the intensity of photons, that is the number intensity of photons, more and more electrons will come out. More and more electrons coming out contributes to more and more current. So the experimental result and the theory what I have explained, both of them have matched. The graph was this, a perfect straight line. More the intensity, more is the photocurrent, and linearly dependent. Okay, next, photocurrent and the potential difference, man. So Now what I am going to do is, I'll just keep the intensity constant. When I say intensity constant, what I am talking about? I am talking about number intensity, man. I am keeping the number intensity constant. And I will, one second, number intensity constant, and I will maintain frequency also constant. That means I am using one particular wavelength light, and the number of photons I am going to send also I am maintaining constant. That means I am not doing any changes to the light which we throw onto the metal plate. I am not doing any changes to the light that is being sent onto the metal plate. Its number intensity is kept constant, the frequency of light is also kept constant. That means I am not changing anything for the light. Now, whatever the electrons that are going to be coming from this cathode plate, they come out, right? And then those electrons which have come out, they will try moving towards the anode one. What the experiment is suggesting us, let's see that first. So the potential difference, let us take this to be the potential difference, or sometimes they'll use that potential. Okay, fine. Versus the photocurrent. Versus the photocurrent. Versus the photocurrent. Okay. Man, they haven't maintained any potential difference. They haven't maintained any potential difference between cathode and anode. So if there is no potential difference, then there is no electric field. If there is no electric field, then the electrons neither encouraged to go towards anode nor discouraged to come. If there is no potential difference between cathode and anode, these electrons, they won't experience any force because there is no potential difference, there is no electric field. Okay. Then one interesting observation is that still there is current. That means the electrons, whatever have come out, they have some kinetic energy. So even if you don't make them go to the anode, they will go on their own because they have kinetic energy. So this current proved that the electrons that are going to be coming out will have some kinetic energy with them. Because when I maintain potential difference 0, when there is no electric field also, electrons are going over there. That's one very important observation. Then what they did is that they kept on increasing the potential difference onto the positive side. So this is encouragement to the electrons. So I'll represent with red. For example, if the anode potential is kept on increasing, if the anode potential is kept on increasing, then automatically you will have electric field like this. Then these electrons will be now experiencing a force. Because of that force, they will accelerate. So there will be more and more electrons reaching in less amount of time, because now they are going to cover the distance faster. Electrons per unit time is going to increase. So is the experiment suggesting that the current is increasing? Yes, the experiment also suggested that the current is increasing, but beyond certain voltage, you can see that the current is getting saturated. So that current is called as saturation current. Why that is happening is that you have maintained a potential difference which is very strong, that almost the electrons which got produced, immediately they are taken away. Now you have to wait for the next round of electrons to get produced or not. For example, for you to understand, every 1 second 4 electrons are getting produced, man. So the electric field is so strong that the 4 electrons which got produced will be taken to here in half second only. So 4 electrons go here in half second. Then next half second you have to wait for the 4 electrons to get produced or not. Once they get produced, again you have to take. So if you overall look at in the 1 second of time, how many electrons are going there means only 4 electrons are going. If you observe microscopically, in the first half second only 4 electrons have gone, next half second 0. On an average, in 1 second, how many electrons are going? 4 only are going. Now you made the electric field even more stronger by increasing the potential difference. Then instead of taking half second of time to go there, now might be they will take 1/10 second. So in 1/10 seconds, 4 electrons have gone. Now in the rest 9/10 seconds, nothing is going to go. So overall, if you see, in 1 second, 4 electrons only have gone or not. So yes, there is a saturation which is going to be reached. No matter how strong you maintain the potential difference, no matter how strong you make the electric field, there will be some amount of electrons which are going to get produced. You have to wait for the next round of electrons to get produced to take them to the anode. Now let us see the other side of it. What is the other side of it? Instead of encouraging the electrons to go, let us discourage the electrons to go. That means the potential of the anode is going to be less than the cathode. Then what is happening, man? There will be force on these electrons to the left side. Now what will happen? They are discouraged to go. That means they are going to slow down. They have a kinetic energy in this direction. How I know that they have kinetic energy in this direction? Because when I don't maintain any potential difference, there is current. That means on their own they are reaching. That means they have some kinetic energy towards the anode plate. But now what is happening? I have applied an electric field which is trying to slow down the electrons, right? Which is trying to slow down the electrons. Okay, fine. Then current obviously has to decrease or not? Yep, current has to decrease. And there is a particular voltage beyond which no electron is able to reach over here. Even the fastest moving electron is slowing down, and before reaching the plate, it will come to rest and turns back. So in that situation, even if the fastest moving electron is not able to reach here, then no current is going to flow because circuit is not complete. And that minimum potential which is needed to stop the fastest moving electron is called as stopping potential. So V naught is called as stopping potential. So what is this stopping potential? What is this stopping potential? It's the minimum potential difference to stop fastest moving electron from reaching anode, from reaching the anode plate. Now look, one important relation I am going to derive. Who is going to, one second, do I have space? No, I don't have. I don't want to mess with this PPT. Okay. One important observation. If you take, this is the electron having maximum kinetic energy. If you are just making it come to rest, that electron is going to come to rest here. It is just coming to rest before the anode plate. Then it turns back. So the fastest moving electron is just stopped from reaching the anode plate. Now if you look at this electron, who is the one doing work on it? Electric field. Okay, work done by the electric field can be written as what? Change in kinetic energy, work energy theorem. And work done by the electric field overall, if you are going to talk about, it is going to be E into V naught. Q times delta V da. Q times delta V is going to be work done by the work done by the external force, minus Q times delta V is going to be the work done by the electric force or electric field. So if you put the signs, you are going to get this. Oh, minus, right? Oh. Minus Q into delta V. Okay. Final kinetic energy is what? 0. What is the initial kinetic energy? Ke max. So we got one very important relation, man. If you want to calculate the maximum kinetic energy of the electron, simple. If you know the stopping potential, you know what is the maximum kinetic energy of the electron. So those who are having a problem, man, it is minus Q into delta V da from electrostatics. What is the charge we are talking about? What is the charge we are talking about? Electron. What is the potential difference we are talking about? Minus V naught. So the whole thing will turn out to be this. I used work energy theorem, and this is very, very, very important. So if they give stopping potential, they have indirectly given you the fastest moving electron's kinetic energy. If they have given you stopping potential, they have given you the fastest moving electron's kinetic energy. Be careful. Very, very, very useful. Okay. From this experiment, like by doing this, what we have understood is at zero anode potential, a current exists. It means that the electrons are emitted from the cathode with some kinetic energy, which I have already explained to you. Right? This second point is irrelevant here, but I don't know, many of the famous coaching institutes as well as books will mention this, but this is irrelevant. Why? I'll tell you. So if you increase the potential, then the electrons are accelerated to go there. So if they're accelerated, automatically what will happen? There is charge moving faster. So charge reaching the anode per unit time charge reaching the anode per unit time increases. Why? The electrons have accelerated, so they move faster, they reach the anode plate faster and in less amount of time. Same charge coming in less amount of time also will increase the current. So saying that as anode potential is increased, current increases, this is correct. But saying that the electrons whatever have come out will have different kinetic energies is wrong. We can't claim like that. If you increase the anode potentials, electrons are encouraged to go towards the anode, they accelerate, they move faster. When they move faster, in less amount of time they reach the anode. So there is same amount of charge reaching in less amount of time, that's why the current is going to increase. Yes, obviously there might be contribution by different kinetic energies also, but what I have said is more logical than this. But why I have picked this point, as I said, many books have written, and it is illogical to say that because of different kinetic energies the current is going to increase. No, ultimately it is because of electrons are encouraged to go towards that side, so they will take less time to go there. So same charge in less amount of time contributes to more current. Okay, after a certain anode potential, current acquires a constant value called saturation current, and the current acquires a saturation value because the number of electrons emitted per second from the cathode are fixed. I said to you, right? Cathode plate, you take cathode plate. From cathode plate, electrons are going to be emitted. The number of electrons coming out from that cathode are fixed. If you are able to take all those in no time, if you take all those electrons in no time, then they go very fast. Then you have to wait actually for the electrons to get created to take them. I already explained that. At a certain negative potential, the photoelectric current becomes zero. This is called the stopping potential, and the stopping potential is a measure of maximum kinetic energy of the emitted electrons, and I gave this relation to you. So this graph is very important because it has given a lot of data. Next graph is going to be, what I am going to do is, onto the cathode plate, I will send the same nature of light. Same nature means same frequency wala. Like if I am sending red light, I will send red light only. But now I will send more intensity red light. That means more intensity. When I say intensity in photoelectric effect, it is what? Number intensity. So first what I'll do, I will do experiment with 100 red photons. Then I will do with 200 red photons. Then I will do with 300 red photons. So basically, I will increase the number intensity, but I'll keep the frequency constant. Okay. Then what's the graph? Then what is the graph? Same thing, man. The potential difference versus the photocurrent. If you use your common sense, if I don't apply any potential difference, if I send 100 red photons, let's say 2 electrons are getting produced. Then if I send 200, you have doubled the photons. Then the number of electrons come also will double. That means now 4 electrons will come. If you triple, 300 if you send, then 6 electrons will come. So 100 photons, 2 electrons, 200 photons, 4 electrons, 300 photons, 6 electrons. So where there is more electrons coming out, when there is more number intensity. So I'll put 3 dots because I am using 3 different intensities. And the graph, when plotted, saturation current for I3 intensity 1, saturation current for I2 intensity 1, saturation current for I1 intensity 1, but all of them have same stopping potential. So this graph clearly proved us few things. Number of photons we throw doesn't matter. It's the frequency which is going to be deciding the stopping potential. Okay, now look, and we know very well that I3 is more than I2 is more than I1. That is the reason why, see, we can clearly see that we got more amount of current when we maintain the potential difference as 0. Why? More intensity photons, sorry, more number intensity means more photons, more electrons, more current. But one interesting thing is that stopping potential is independent on or independent of intensity. Okay, one important thing. And one more thing is that I can claim that as I maintain same frequency, stopping potential will depend on the frequency. Makes sense also. We will talk about this part in detail in future. Future in the sense some 2-3 slides from now on. What we realize is that the saturation current increases with increase in intensity. Obviously, man, more number intensity, more electrons are going to get produced. More electrons gives more current. Okay. Second thing is that the stopping potential is independent of the intensity. Man, if you talk about the maximum KE, the maximum KE is E times V naught. So if the stopping potential is going to be independent of intensity, the maximum kinetic energy of the electron also is independent of intensity. A very important thing. Next. Now what I'll do is, I will throw same number of photons. but of different frequencies. I'll throw yellow light, I'll throw blue light, I'll throw orange light, I'll throw red light, like that. So I'll send different frequency wala, but same number of photons. So intensity, I'll maintain the same. Intensity, I'll maintain the same. Then the graph is going to be something like this. All of them have same saturation current. And this is the potential difference we are talking about. And now let us take this is having minus mu naught 1, and this to be having minus mu naught 2, and this to be having minus mu naught 3. Okay. Which one is having more stopping potential? This one. But do they have same saturation current? Yes. Okay. Now, if stopping potential is going to be more, that means you have to struggle hard to stop the fastest moving electron. More stopping potential, more kinetic energy of that fastest moving electron. Right or wrong? That means that electron is getting more energy in the form of kinetic energy. That means the photon which is going to strike it should have more energy. More energy photon only can give more kinetic energy to the electron. So if I take the frequency of this is mu3, and which has struck the metal plate is mu2, and which has struck here is going to be mu1, then I can say clearly that mu3 is more than mu2 is more than mu1, because I can see that the stopping potential is more for 3, so more energy photon should have stuck. More energy photon should have stuck. Okay, this is one graph. Next, let us plot one last graph, man. One last graph. Because from this graph I clearly realize that stopping potential is going to depend on frequency. Now I want to study more about it. So how the stopping potential is going to change when we are going to be changing the frequency. So that graph was plotted. So they kept on changing the frequency and they were measuring the stopping potential. In fact, I don't need to draw this side. This is the stopping potential. This is the stopping potential. And this is the frequency of light that they have used. Now, man, when the graph was plotted or when the experiment was done, they used different frequency of lights and they were calculating the stopping potential. And the graph came out to be something like this. And this frequency is called as threshold frequency. So below that frequency, can you see a graph? No. Why don't you see a graph? Below that frequency, no electron only is coming. If there is no electron coming, why do you need to stop? What is stopping potential? Stopping potential is the potential difference you have to maintain to stop the fastest moving electron. If electron only is not coming, then what you will stop, man? So we can clearly see that when the frequency is less than certain frequency, that is what we are calling as threshold frequency, I don't see a graph. No photoelectric effect. It is contradicting wave theory. What wave theory says? You throw energy onto the metal plate. If the energy is weak, if the intensity of that light is weak, then weak electric field will be there, weak oscillations, but Might be after 1 year or might be after 2 years, definitely there will be photoelectric emission. But what the graph is suggesting, graph is clearly suggesting that if the frequency of the light is less than certain value, no electron will come out. Experiment is suggesting this. So now you think of that plastic ball and water bottle thingy I was explaining. This is not premier, man. See, in the beginning of the class, people said that, sir, don't reply to the comments. It will break the flow. That's why I'm not replying to the comments. This is live. This is live. I can read Yashoda Miska, right? Rakesh said hi, long back. So this is going to break the flow. That's the reason why. Yes, it's a live, Baladhar CH. It's a live. But those who are going to seriously listen and seriously writing, now for them it is going to be a problem. The flow will break. That's why I'm not looking at the comments. But it's a live. Okay. Mostly whatever the sessions I take, it will be live. I won't come on recorded videos. It's live all the time. So what I'll do is, might be some 1 hour at a stretch, properly I'll do theory and then I'll look at the comments. Okay, fine. See, I broke the flow. Okay. Below certain frequency, no photoelectric effect. Think of that water bottle and the plastic ball I have given. So if the plastic ball has certain amount of energy, only it can make the bottle fall off. If the plastic ball has less energy, it can never make the bottle fall. That means it can never make, if you replace the plastic ball with photon in your brain and water bottle with electron, then that photon can never make the electron come out. So who is succeeding in explaining the photoelectric effect? Clearly photon theory is explaining. Wave theory is clearly failing. Right? Okay. No, this is not horror class, man. I'm so involved in teaching. How can you call it as horror class? Just because me not smiling, you don't need to call it as horror class, idiot, Matthew. Stopping potential is found to vary with frequency of incident light linearly. Yes, graph was straight line. Okay. Greater the frequency of incident light, greater the stopping potential. Yes, you can see that. If you want, I can mark it also. We can mark it also. So more is the frequency, more is the stopping potential. Okay, next. There exists a certain minimum frequency below which no stopping potential is required as no emission of electrons takes place. This frequency is called threshold frequency, mu th. And for your kind information, man, this mu th, whatever is there, is also going to have some lambda th, because you can convert it, na? So if the frequency is less than the threshold frequency, or if the wavelength is more than the threshold wavelength, in both the situations, both of them are actually same. No electron emission. No electron emission. That's it. Okay. So the failures, just go through. I have been keep on explaining this. Just go through. I was doing this all throughout the class. Okay, lighting placement makes it weird. Man, I think in Chrome I have to open it in dark mode or something. The Chrome part is having a reflection here, man, Matthew. Yes, next week we are going to do waves. Meanwhile, people just go through. I have kept on explaining this from long time. Meanwhile, people go through, yes, next week we are going to do waves. So this week I will complete modern physics. So the tomorrow's class is going to be on atoms. Tomorrow's class is going to be on atoms, right? Nuclei and all those things, I'll do a separate video. But yes, you people can do photoelectric effect, dual nature. Today I'll complete that. Next class is going to be on what we call atoms. I'll complete the whole atoms. If possible, if I can squeeze in, I'll squeeze in nuclei also. And then next week is going to be waves. Complete waves will be done. Complete waves will be done. Okay. Already I have been keep on saying that. Now look, man. Einstein has explained the photoelectric effect with his equation. Okay, what did he say? He is a fan of conservation of energy, man. He is a fan of conservation of energy. See, look, we have a photon, right? Let me draw it. See, we have, let's say, a photon. This photon dude is going to go and strike an electron. It might be an electron in the outermost orbits, or it might be an electron in the innermost orbits, whatever might be the case. Whatever might be the case. So this photon, let's say, goes and hits this, and it gives the energy to it. So from conservation of energy, always keep in mind the photon interactions. In photon interactions, you can conserve the energy as well as momentum both. Okay, fine. Now I'll talk about conservation of energy. Not I. Einstein was talking about conservation of energy. Mohammed Naufel, sir, SHM damped oscillations and all not done. It has been removed, man. For JEE means it has been removed. For that reason, we haven't done it. When JEE advanced comes closer, I'll do damped. Okay. So whatever the energy of the photon is there, it is given to the electron. So now electron got that energy. Got it. Electron has got that energy. Now that energy, whatever it has got, electron will use it in two ways. One, to come out. Rest will be in the form of kinetic energy of it. So some energy it will use to come out. And rest is going to be in the form of kinetic energy of that electron. So Einstein is the first person to say that the electrons that are going to be coming out can have energies ranging from 0 to KE max. Why? Because if the photon is going to strike inner electrons, then those electrons are strongly bound to the nucleus. So for them to become free, they need to use majority of the energy to become free. So if the energy used to come out is more, then automatically they will have less kinetic energy stored with them. There will be some electrons which are going to be loosely bound. If the photon is going to give energy to those loosely bound electrons, they take least energy to come out. Rest all will be in the form of kinetic energy, right? So when we talk about energy of the photon, anyway that is fixed, because the energy, the photon we are sending is fixed. Now if that photon strikes an electron which is in the outer orbits, then the energy it needs to come out is minimum, then automatically there will be more energy stored in the form of kinetic energy. Then there is more energy stored in the form of kinetic energy. So if you want to talk about the fastest moving electron, the fastest moving electron which is going to come out is that electron which is there in the outermost orbits, which is very weakly bound. So the weakly bound ones or in the outermost orbits, those are the ones which are going to come out with maximum kinetic energy, and the minimum energy needed for them to come out is also going to be called as work function. I'm going to introduce a letter called as phi, which is what? work function, you people already know majority of you are going to be either droppers or you are in 12th. Okay, what is it? It's the minimum energy needed to come out. It's represented with the symbol phi. Then the energy of the photon, whatever is there, is going to be work function plus Ke max. So I can write the very same thing as what? Hc by lambda, which is energy of the photon, is going to be work function plus, can I write EV naught? Yes. Now, man, you try rearranging this one. Then what are you going to get? V naught is going to be Hc by lambda, right? H mu we can write it. So I can write it as H mu by E minus phi by E, which is very important, man. Why? Do you remember the graph between stopping potential and the frequency? If you remember, it was a straight line and you can clearly see that the intercept was negative. Do you remember the experimental graph? Why the intercept is negative? You only see, is the intercept negative? Yes. What is the value? What is the value of this? Minus phi by E. And what is the slope, man? If I am going to take theta, tan theta is H by E. And for your kind information, it's Planck's constant charge of the electron. That means no matter which metal plate you take, slope should be same or not. Why? Depending on the metal plate you take, work function of that metal plate might change. But Planck's constant is same for every material and charge of the electron is going to be same for every material. So slope is independent of the material. So every material should have same slope but different negative intercept. Okay, fine. The graph is very well explained. Now look, one more important thingy. If the photon I send is of threshold frequency, if the photon I have sent is of threshold frequency, then the electron is given bare minimum energy for the electron to come out. Then there is no energy stored in the form of kinetic energy, because you are talking about threshold frequency. That's the least energy that you can give such that there will be photoelectric emission. So the electron will just come out. It will not have any kinetic energy. So sometimes instead of giving work function, they give threshold frequency or they'll give threshold wavelength. So from threshold wavelength and threshold frequency, you will be able to calculate the work function. You'll be able to calculate the work function. Okay, fine, nice. Now, let us talk about some questions. And one more thing, man. 90% of the times, work function will be given in electron volts. And energy of the photon also should be written in electron volts. But when you are going to use the formula Hc by lambda, you get the energy in joules. So you should know the ready-made formula See, energy of the photon is going to be hc by lambda, and if you put hc, you will get in joules. If you convert it into electron volts, it is roughly 12,400 electron volt angstrom by lambda, roughly. So memorizing this will be helpful for you if they don't give the hc value. But what I have noticed, if it is JEE advanced, every time, almost every time they have given the hc value. If it is JEE mains, almost every time they have given the hc value. Sorry, JEE advanced. If it is JEE mains, majority of times they have given the hc value. You don't need to take this. You take what they have given. You can see I have put hc as this, right? You don't need to take this one if they have mentioned it in the question. Now look, did they mention it? Yes. Did they mention it? Energy of the photon, they asked us to take it to be 1237 by lambda, and lambda should be put in nanometers. So basically they could have clearly written like this. They could have written it is 1237 electron volt nanometer by lambda. So if the lambda is put in terms of nanometer and this nanometer will get cancelled out and you'll get energy in terms of electron volt. Nanometer will get cancelled out and you'll get energy in terms of electron volt. If it is going to be given in angstrom, then if you put lambda in terms of angstrom will get cancelled out and you'll get energy in terms of electron volt. Okay. So let us do this question. Sinpu. See, you need to have bare minimum Mazda. You have to pick at least some 3-4 chapters and you have to learn them. Otherwise, getting with the 2 subjects is going to be slightly difficult. Okay, da? In a photoelectric effect experiment, threshold wavelength is given. Why did they give threshold wavelength? Because they won't give information about work function. That's why they gave. Okay. If the wavelength of incident light is 260 nanometer, the maximum Ke, man, what did Einstein say? hc by lambda, energy of photon, is work function plus the Ke max. And the work function can also be written as what? Can also be written as hc by threshold wavelength plus the Ke max. Okay, nice, good. Now we have to do math. Okay, let's do it. See, I will do cheating now. I am going to do cheating. I am allowed to do that because I am not giving examination. So I will not put my brain under stress for calculations. I will simply open my phone. I will do the calculations with the help of phone. So 1237 by, what is the wavelength they have sent? 260. By 260 gives it in electron volts because nanometers will get cancelled out. Is going to be 1237 divided by 380 plus the Ke max. Now 1237 divided by 260 is 4.757 is going to be 1237 divided by 380 is going to be 3.255 plus the Ke max. So now if you observe properly, roughly the maximum Ke is coming out to be 1.5 electron volt or not. So which option? Option 1. Which option? Option 1. Okay. Next. A photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and wavelength lambda by 2. If the maximum kinetic energy of the emitted photoelectrons in the second case is 3 times the first case, they are asking you work function. You have to write the equations twice. Learn to write them. Look, if we talk about the solution, first hc by lambda, is the energy of the photon, E is work function plus write it as some K. Ke max, you write it as K. Now hc by lambda by 2, what is the work function? Work function obviously will remain the same, but what is the kinetic energy? 3 times the first case, that means it is 3K. Right? So from here, can you get the K value? Yes, the K value is going to be hc by lambda minus 5. Put it over here. Then you have 2hc by lambda is going to be 5 plus 3 times hc by lambda minus 5. Now, what do you get? You get hc by lambda to be equal to 2.5. So the phi value is hc by 2 lambda. Which option? First option. JEE Mains 2016. Very good Sagar. Very good Sagar. Next to this. And one more thing, I will focus more on 2019, 20, 2018 like that, because the pattern is going to be similar to those days, and the level also might be of those days. That's why I'll focus more over there. The stopping potential V naught as a function of frequency mu for a sodium emitter is shown. The work function of sodium from the data plotted. Look, you can clearly see that the threshold frequency is 4 into 10 to the power 14. So threshold frequency is 4 into 10 to the power 14. Okay. Fine. Now what they are asking? Oh, they are asking work function, right? Do you remember work function in stopping potential in this graph? If you remember, what is the negative intercept? This is going to be minus phi by E. All you have to do is just extend and see what is the intercept. Just extend and see what is the intercept. You can see that when it is going to travel 2, it is increasing by 1. So if you travel to this side, it will decrease by 1 second. Got screwed. I'll explain why we got screwed. This is not 0, da. That's not 0. So somewhere over here we will have it. So we have to find it where this is going to come and meet. If you use, for every 2 there is an increase of 1 stopping potential. So for every 2 there should be a decrease of 1. So for 4 there should be a drop of 2. If you go from here to here, it will decrease by minus 1. If you go from here to here, it will further decrease by minus 1. So this is going to be what? Minus 2. So minus 5 by E is 2 volt. Minus 5 by E is minus 2 volt. So write it minus 5 by E. So from this data and from this data, minus 5 by E is minus 2. So the work function is going to be 2 electron volt. Mark the closest one. Mark the closest one. I think the data is not properly plotted. If it is properly to the scale, then pakka for sure it should come out to be exactly 2. JEE Mains 2019, and we have questions from JEE Advance also. Look, these kind of questions, if you see them, don't be scared of them. They are easy, they are not difficult. Look, they are indirectly giving you what is the angular frequency. If you know the angular frequency, can you get the frequency? Yes, you can get the frequency. Right? So In photoelectric effect, we need frequencies. Keep that in mind. In photoelectric effect, we need frequencies. And they haven't given the frequency, but they gave the angular frequency. Coefficient of T is going to be omega from waves chapter. So we have two waves here. One wave is having angular frequency 3.14 into 10 to the power 7 into C man, which is pi into 10 to the power 7 into C. So what will be the frequency then? Frequency is going to be omega by 2 pi, right? So the frequency is going to be omega by 2 pi. Actually, I don't need to calculate this first one because they are talking about maximum kinetic energy. They are talking about maximum kinetic energy. When they talk about maximum kinetic energy, what we have to do, sir? We have to go for maximum frequency photon. Here, who is having more frequency? This fellow has more frequency. So there is no point in calculating the frequency of the first one. Directly go for the second one. Omega 2 is going to be what? 2 pi into 10 to the power 7 into C. Right? So if you talk about the frequency in the second case, it is 2 pi into 10 to the power 7 into C divided by 2 pi. 2 pi gets cancelled out. Now C is going to be 10 to the power 8. So you will have 3 into 10 to the power. The frequency is going to be 3 into 10 to the power 15. Okay, but I need wavelength. So the frequency can be written as what? C by lambda. So lambda is going to be what? C by F. So which is going to turn out to be how much? 1 by 10 to the power 7. Which is going to be how much? 1000 angstrom. So the wavelength is 1000 angstrom. And did they mention the Hc values? No. So let us roughly take it. So what is the energy of this photon? The energy of this photon is going to be Hc by lambda, right? Which is going to be 12,400 electron volt angstrom divided by 1000 angstrom. Ding, ding. So 2 zeros, 2 zeros. So you get roughly 12.4 electron volt. So the energy of the second part of the beam is 12.4. Work function 4.7. If you want maximum Ke, energy of the photon minus energy of the photon plus, energy of the photon is equal to work function plus Ke max. So that's it. So what will be the Ke max then? The Ke max is going to be 12.4 minus 4.7, which will be around 7.7. So you check which is around 7.7 thingy, mark that. Option 1. So what you have to realize over here, whenever they give magnetic field equation, whenever you see electric field equation, don't be scared of them. Let the expression be as big as possible. It's fine. You find the angular frequencies that are involved, and from the angular frequencies get the frequencies. Once you know the frequency, you will know the wavelength. Once you know the wavelength, you will be able to calculate energy of the photon. We ultimately need energy of photon. That's it. Okay, super. Let us go for the next. JEE Advanced 2013 question. What they are asking? Work functions of silver and sodium are 4.6 and 2.3 respectively. Ratio of the slope of the stopping potential versus frequency plot for silver to that of the sodium. This is one of the easiest. What are they talking about? They are talking about stopping potential versus frequency graph. Do you remember what I said to you? It's a straight line, and if you remember, the slope slope was h by E, man. It's Planck's constant by E. The slope is constant. It is independent of the material we are talking about. So whether it is silver or whether it is sodium, whether it is gold, whether it is platinum, whatever it is, man, blindly I can say that the slope is going to be same for all of them. So the ratio of slope will be what? 1. So the ratio is going to be 1. As simple as that. As simple as that. So it's a JEE Advanced 2013 question. All you need to have is some conceptual clarity. Yes, which one will depend on the material intercept. The intercept is going to be minus phi by E. Work function is contributing for the intercept. Now if you ask me which one is going to have more negative intercept, then silver will have more negative intercept than the sodium. So if they are going to ask which graph belongs to what, for example, they have plotted 2 graphs like this, and if they are going to ask which line belongs to sodium, which line belongs to silver, look, okay, just a second, I will draw this with a different color for more clarity. Now if you extend it, this is the intercept, and if you extend this white one, this is the intercept. Which one has more negative intercept, man? Which one has more negative intercept? Obviously the orange one, whatever I have drawn, right? And negative intercept depends on work function. Which one has more which one has more work function? Silver has more work function. Then automatically this line will belong to silver and this white one will belong to sodium. Is that clear, everyone? Okay, super. Next. One more JEE advanced question. What did they say? A metal surface is illuminated by light of 2 different wavelengths, 248 and 310. The maximum speeds of the photoelectrons corresponding to their wavelengths are U1 and U2 respectively. If the ratio of U1 to U2, man, U1 to U2 ratio is 2:1, then kinetic energy ratio is going to be 4:1 or not? Simple. And which one will have more kinetic energy? Obviously the one which has less wavelength. Less wavelength photon, if it is sent, it has more energy, so more kinetic energy. Okay, first case. Man, look, JEE Advanced, right? Look here, they mentioned. So let us talk about the first case. When we talk about the first case, it's 1240 electron volt nanometer by 248 nanometer. So nanometer gets cancelled out, you will get energy in electron volt. And what are they asking? Work function. And the kinetic energy, let's take it K1. Take it K1. Now what is the second case? Okay, let me simplify it a bit. As I said, I have the freedom to use calculator. You don't have it. And that too, it is JEE Advanced. That's why they are asking you nearly. You don't need to calculate so deep and get the exact values like JEE Mains. Okay, 1240 by 248. 1240 divided by 248, which is turning out to be 5. I love JEE Advanced. Look at the calculation, man. So simple. It was 5. Now let us go for the second case. Shit. I didn't take one extra slide. So when I go for the second case, what is the second case, sir? Directly I'll write it. 1240 by 310. 1240 by 310 is going to be the work function plus K2. Work function plus K2. Okay. 1240 by 310 will be how much? It's going to be 3, right? Common sense. calculation part is, sorry, 4. And now you tell me K2 can be written as what? K1 by 4, or you just write the K2 one, and from here the K2 is going to be 4 minus 5. Can I put this here? Because K1 is 4K2. Write it. 5 is equal to 5 plus K1 is 4K2. So 4 times K2, which is 4 minus 5. So 16. 16 if it is going to go this side. 5 minus 16, which will be what? Minus 11. So minus 11 is minus 3, 5. So 5 is going to be 11 by 3, which is going to be less than 4. Option A. Option A. Okay, super. Next. This is one of the best question, and majority of the people were not able to mark it during that year. During that year, 2009, although it's a 2009 question, you get to learn a lot from this. Photoelectric effect experiments are performed using different metal plates P, Q and R having work functions 2 electron volt, 2.5, 3 electron volt. A light beam containing wavelengths of 550, 450, 350 with equal intensities illuminates each of the plates. Correct IV graph for the experiment is. They asked you to take this. So let me write the whole data. Man, what are the plates we are talking about? P plate, Q plate, R plate. So let me write it. The P plate, the Q plate and the R plate. So what is the work function of this P plate? Work function of this P plate 2, 2.5 and so 2, 2.5 and 3. Okay, nice, good, fine. Now look there. All the 3 plates P as well as Q as well as R are getting 3 different lights, 550, 450, 350. Now I need to see what are the energies of those things. Let us keep aside. Let us talk about the energy of the 551. Energy of the 551. So if I talk about energy of the 551, let us talk about Hc to be how much? 1240. So write it 1240 by 550. So what is the energy of this? Energy of this photon? 1240 divided by 550, which is 2.25 roughly. Now let us talk about energy of 451. So 1240 divided by 450, which is 2.75. Okay, and then if you talk about the 351, it is 1240 divided by 350. So 1240 divided by 350 is going to be 3.54 something. Now look, let us talk about P. P, it needs minimum energy of 2 electron volts to emit electrons. Can 550 emit electron when thrown onto P? Yes. And this 550, let us take, has intensity I. And then this also should have I intensity. Then this also should have same intensity, which is I. Why? They only mentioned it. With equal intensities illuminates each of the plates. 550, 450, 350 have equal intensities. Okay. Now look, for the plate P, all 3 of them can emit. So what is the total intensity that is contributing for emission of electrons? 3I. For plate Q, can this emit? No. Can these 2 emit? Yes. So what is the net intensity that is contributing for electron emission? 2I. Now for R plate, 3 electron volt, right? Only this one is going to contribute. Now you tell me, which plate has more intensity? The plate P has more intensity. And which is going to have fastest moving electron? Look, 3.54 and 2, less work function, and this energy is highest. So 3.5 minus 2, so the KE max in this case that you can get is roughly 3.5 minus 2 is 1.5, okay, 54. So what is the KE max that you can get here? The maximum energy one is 3.54 minus 2.5, which is 1.04. And if you are going to talk about the KE max that you can get here, 3.54 minus 3, which is going to be what? 0.54. So maximum KE needs maximum stopping potential. So stopping potential should be highest for P. And saturation current should be highest for P because 3I intensity is contributing. Look at the graphs now. Stopping potential highest for P. And saturation current also should be highest for P. Which graph? This graph. Saturation current highest, stopping potential also highest. That's why I said this is one of the best question. That's why I said this is one of the best question. Okay. You get to learn a lot. Okay, now look, what did D-Broglie say then? Man, light is having dual nature. YDSC proved that there is wave nature with it, and photoelectric effect proved that there is particle nature to it. Then D-Broglie came up with some hypothesis. He is like, Mother Nature is not biased. Mother Nature is not biased. If for radiation Mother Nature has given dual nature, even matter means nothing but me, you, electron, the table, this pencil, this board, all these are matter. So even matter should have dual nature. Then he is like, okay man, wavelength, okay, one second. Momentum of photon is given by h by lambda. So let us take lambda to this side, and then the wavelength of photon is going to be given by h by p. So if it is a matter, then the momentum of matter we know. What is the momentum of the matter, man? Momentum of the matter is m into v. Then he said, okay, this is the D-Broglie wavelength. This is the D-Broglie wavelength for matter waves. That's what he said. It's a hypothesis. Later people proved that yes, matter can exhibit wave nature also. Davison and Germer experiment proved the electrons have wave nature, or wave nature of electrons has been proved in Davison and Germer experiment. And the experimental results and whatever D-Broglie has given, both of them have exactly matched. So whatever this fellow has proposed, it's true. Okay. Now, will we always have momentum? Sometimes they might give kinetic energy, right? And what about that kinetic energy then? See, when I talk about the kinetic energy can be written as half mv square. So to this one, I will multiply mass and I will divide mass. So from here, m into v can be written as root 2 mke. Then what will be the wavelength? It is going to be h by under root of 2 mke. This is going to be very helpful for you. Okay, fine. Now, sometimes do you know what they do? They take charged particles and they are going to talk about the kinetic energy. So before we go for those charged particles, this is the De-Broglie hypothesis. Lambda, see where we have started, he started with momentum of photon, and then he took the wavelength to the left side, then the wavelength of the photon is going to be h by p. So if we talk about matter, momentum of matter is m into v, and that m into v can also be represented in the form of kinetic energy of the matter. This is the basic theory. Now, if we are going to talk about charged particles, charged particle accelerated through a potential difference. Look, this is a point and this is a point, and the potential difference across these 2 points is some capital V, big capital V. And whatever the charge I am talking about, the charge whichever I am talking about, this charge is initially at rest, and now it is accelerated through a potential difference. Then obviously when the charge is going to be accelerated through a potential difference, charge q and mass m, when it is accelerated through a potential difference, it will gain kinetic energy, right? Okay, so then work done by all the forces is going to be what? Change in kinetic energy. Obviously the work has to be positive, so without explaining anything, I can simply write work is going to be q times the potential difference v is going to be the final kinetic energy minus the initial is anyway 0. So the kinetic energy can be written as what? Q into v, where v is going to be what? Where v is going to be what? V is going to be the potential difference across which the charge is accelerated. Okay, so we can also write the wavelength, De-Broglie wavelength for charged particles. Although I have put slides in future, I have done it here only so that you people will have a proper understanding of it. In a flow I have done everything. In future I have put slides. There I'll directly write this formula. But keep in mind, if you have to use this formula, the charge should be accelerated from rest. Initial kinetic energy has to be 0. Initial kinetic energy has to be 0. Okay. Initial kinetic energy has to be 0. Yes, change in, that is what I have represented with capital V, man. Accelerated through a potential difference of V. Accelerated through a potential difference of V. I'm not bothering about signs. Anyway, I use the word accelerated. Obviously, one second. If you want me to write it with proper signs, I can do it. It's not a big deal. If you want me to write it with proper signs, it's not a big deal. Okay, I'll go step by step. It's perfectly fine. Now, if this charge has to accelerate, pakka there should be electric field like this. So, if I am going to say this to be at V1 potential and this to be at V2 potential, the potential difference V1 minus V2 is what I am writing as capital V. So, the change in potential is going to be minus capital V. Why? Change is going to be final minus initial. Final minus initial. As I said, charge is accelerated, for sure electric field should be like this. Now, what the work done by all the forces, only electric field is doing work, right? Work done by the electric force is going to be what? Minus Q times delta V. So minus Q into what is delta V? Minus capital V, which will turn out to be what? This only, na? So that's why instead of doing all this calculation, I simply said it is accelerated. That means work done is going to be positive. If work done is going to be positive, only then there will be increase in kinetic energy. So that's why without explaining all this, directly I wrote it. But now you should have understood properly. Okay, fine. Let's do a question. Find the ratio of De-Broglie wavelength of proton and alpha particle which have been accelerated through same potential difference. First of all, we need to talk about a formula which is going to involve the potential difference. The big V here is representing the potential difference through which it is accelerated. Now V is same, H is same, 2 is same. So I can say the wavelength is inversely proportional to root mq. Then they are asking what ratio of proton to alpha. So proton to, if you want alpha, then it is going to be root m alpha q alpha by mp qp. Mass of the alpha particle is 4 times the mass of the proton. Charge of the alpha particle is 2 times the charge of the proton divided by mp qp, which will result in what? Root 8, which is 2 root 2. Which is 2 root 2. Okay. Next. A particle moving with kinetic energy E has de Broglie wavelength lambda. If the energy delta E is added to its energy, the wavelength becomes lambda by 2. Okay, man. De Broglie wavelength is h by under root of 2mke. Right? And now, what happened? De Broglie wavelength became half. What did you do? You have just added delta E energy. That means now the kinetic energy is E plus delta E. So can you write, just a second, Ke, we are writing it as E. Put the lambda over here, then it is going to be h by 2 times root 2m into E is going to be h by root 2m E plus delta E. H root 2m also you can cancel out. Let's do the squaring. Then you will have 1 by 4e to be equal to 1 by e plus delta E. From here it is very evident that the delta E should be equal to 3 times E. So if you increase the energy by 3, then the wavelength will become half. De Broglie wavelength will become half. Okay. Next, JEE Mains 2020 online thingy. JEE Mains 2020 online thingy. An electron and a photon have same energy E in the range of eV, electron volt. The ratio of de Broglie wavelength associated with the electron and the wavelength of the photon. They are talking about two different things. Electron is matter, photon is not matter, right? And if you talk about the wavelength of the photon is going to be energy of the photon. One second. Let me write step by step. Energy of the photon is hc by lambda. So wavelength of the photon can be simply written as hc by E, right? Now they are talking about electron and they say that they have same energy E. So if I am talking about the wavelength of the electron, it is h by root 2 times mass of the electron into kinetic energy of electron. So that kinetic energy I am taking as E. Now they are talking about the ratio. So lambda, de Broglie wavelength of the electron to de Broglie wavelength, sorry, not de Broglie wavelength, wavelength of photon is going to be h by root 2me by hc by E. So h and h are going to get cancelled out. So you are going to have E by C root 2me. So you get 1 by C into root E by 2m. You only mark which option. 1 by C E by 2m to the power 1 by 2. Okay. Next. IIT JEE 2010. JEE Advanced 2010. Okay. Now look. An alpha particle and a proton are accelerated from rest by a potential difference of 100 volt. Both of them are accelerated by same. After this, the De-Broglie wavelengths are lambda alpha and lambda p respectively. The ratio of lambda p by lambda alpha to the nearest integer. They are accelerated through same potential difference. De-Broglie wavelength is h by root 2m Ke, and that Ke can be written as what? That Ke can be written as what? Q into V. So you can say lambda of P by lambda of alpha to be mass of alpha, charge of alpha by mass of proton, charge of proton. I already did this in this class. It is root 8, which is going to be 2 root 2. So it is going to be 2 into 1.414, which is going to be roughly 3. Integer 3. Now look, in some lower level examinations, not on mains level, like if the question is going to be too easy on mains level also, or on CET levels, let's say for example KCET or any CET examinations, Karnataka CET or Tamil Nadu CET or Andhra EPSET, whatever it is, in all those examinations, if you can memorize these things, it will save time for you, especially this one, wavelength of electron. Why? Look man, if you are going to talk about the de Broglie wavelength, it is h by under root of 2mq into the capital V. Capital V is the potential difference. Capital V is the potential difference. Okay, now look. If I am talking about electron, then de Broglie wavelength of electron, Planck's constant will be same, 2 times mass of the electron, charge of the electron into V. So as this whole part, as this entire part, whatever is there, this entire part, it's a constant for the electron. Now we have to talk about through how much potential difference we are accelerating it. So as this is a constant, we have put all the values and we got this. And trust me, some 3-4 times I have seen in CET examinations, if electron is accelerated through, if the electron is accelerated through 100 volt, what is the de Broglie wavelength? So it's very simple now. As we already know the formula, 12.27 by root 100 angstrom, which is going to give you 1.227 angstrom. As I said, mostly wavelength of electron is going to be needed. Okay, next, let us talk about some questions on it. De Broglie wavelength of electron when accelerated by 50 volt. 2015 JEE means they have asked. So the de Broglie wavelength is 12.27 angstrom divided by root 50. Root 50 is roughly equal to how much? 7 man. Roughly equal to 7. So 12.27 by 7, which is going to be what? Less than 2 and close to 2. So you can mark 1.7 angstrom. So all these questions they have asked. Now, sir, are we going to come across only charged particles? Are we not going to come across other particles? No, we can come across. We can come across but JEE mains nor JEE advanced has focused on this part till now. They can ask. What kind of questions they are going to ask? Look, find the de Broglie wavelength corresponding to the root mean square velocity of hydrogen molecules at room temperature. First of all, you get the RMS speed, which is going to be root 3 RT by M. So root 3, 8.314 is the gas constant, temperature is going to be 293 divided by the molar mass. Hydrogen is going to be having 2 grams for 1 mole. So you can write it as 2 into 10 to the power minus 3. You should calculate this whole thing. Right? Now you got the velocity. For this velocity only they are talking about. So the wavelength of this particular hydrogen atom, or you can say molecule, hydrogen molecule, lambda is going to be h by mv. Man, here m is mass of hydrogen, the molecule. You should not put it as 2 into 10 to the power minus 3. 1 mole of hydrogen sample is going to be 2 into 10 to the power minus 3. But each hydrogen atom is going to be different. You have to calculate. Avogadro number of hydrogen atoms will have 2 into 10 to the power minus 3. Then each mass is going to be having, like each mass of hydrogen, you have to find it from there. So we know the H value. You know how to calculate the mass of the hydrogen atom. We know the V value. Now we get the De-Broglie wavelength or not. Sometimes they are going to talk about average. Then it is going to be root 8 RT by pi m. Sometimes they'll talk about most probable, root 2 RT by m. So yes, especially for mains they can ask this. And one more thing, man. If this part is asked in the numerical of mains, if they are going to ask this in the numerical of mains, leave it. Why? Look at the calculation, man. And in the numericals of main, you have to go up to 2 decimal places. Who will do this calculation? So if you are spending time with this, you are losing marks. So in mains, when there is no choice, especially with the numerical questions, you need to know when you have to leave the question, because no one in the examination will be able to do the square root of this and get it up to 2 decimal places exactly. Unlike JEE Advanced, mains won't even give range for the answer. They want exact answer. So the probability of you getting an answer up to 2 decimal place, correct up to 2 decimal place, is 0.000000001. So it's very rare. So if it is going to be given in MCQs, then definitely do try it. JEE Mains 2020. JEE Mains 2020. Aishwarya, yes, this is physics. Now, when photon of energy 4 electron volts strikes the surface of metal A, the ejected photoelectrons have maximum kinetic energy Ta and De-Broglie wavelength lambda A. Okay. Kinetic energy they mentioned as Ta. De-Broglie wavelength is going to be h by root 2m kinetic energy, which they mentioned as what? Ta. Okay. Now, if you talk about the second one, the De-Broglie wavelength lambda b is h by under root of 2m Tb. Okay, fine. Now they gave the relation. Lambda b is 2 times lambda a. So h by root 2m Tb is going to be 2 times h by root 2m Ta. Now if you do the squaring, what are you going to get? If you do the squaring, what are you going to get? 4 Tb is going to be equal to Ta or not? Yes. And they said that TB is Ta minus 1.5. So from here, TB is going to be 4 Tb minus 1.5. So TB from here will turn out to be 0.5. Okay. So the TB value is 0.5 electron volt. Okay. Now they are asking work function of metal B. And what is the energy of photon they are sending? 4. Okay. Man, energy of the photon we are going to send is going to be work function plus the Ke max. What is the energy of the photon we have sent? 4 electron volt. What is the maximum kinetic energy? We got it to be 0.5. Then the work function is going to be how much? 3.5 electron volt. It's 3.5 electron volt. Okay. Next question. JEE Advanced 2017. JEE Advanced 2017. Yes, we are almost done. We are almost done, Aishwarya. We are almost done. This is the last question, in fact. As far as I remember, yes, this is the last question. This is the last question. We are done with dual nature and matter. Up to advanced level, you will be able to easily manage. Up to advanced level. If you don't trust me, you start solving the advanced questions. If you pick 10 advanced questions in your first go, you will definitely get 6 advanced questions. In your first go, definitely you will get 6 advanced questions. JEE means almost every question you will get after the theory that I have given. Mission JEE. Hello sir, how are you? The last question, man, come on fast. A photoelectric material having work function phi naught is illuminated with a wavelength. Okay, that means the wavelength that is illuminated is less than the threshold wavelength. Hc by phi naught is threshold wavelength. That means photoelectron emission will take place. The fastest photoelectron has a D-Broglie wavelength lambda d. Okay. A change in wavelength of the incident light by delta lambda results in change delta lambda d in lambda d. See, whenever they are going to talk about delta lambdas and all those things, as far as modern physics is concerned, you go for differentiation. Differentiation gives you small changes. So the small changes, that is d lambdas, d lambda d's, you can put it in delta lambda d's, right? So look at the options. The options are not so complicated. That means they have definitely used differentiation into it. That's how you are going to be realizing. Okay. Now look. I won't give the complete solution of this. You can do that. The D-Broglie wavelength is going to be h by root 2m times the kinetic energy. Root 2m times the kinetic energy. Okay. Now we need kinetic energy. And the kinetic energy, if you are going to talk about energy of the photon is going to be the work function plus that kinetic energy. So that kinetic energy can be written as what? Work function minus energy of the photon. Energy of the photon can be written as hc by lambda. Energy of the photon can be written as hc by lambda. Yes. Now you put it over here, and then you have to differentiate. So the lambda d, whatever is going to be there, is what? H by root 2m Ke thingy, right? You differentiate. Kinetic energy is going to change if you are going to be changing the wavelength. You can get that relation. How? Look, man, you differentiate this Ke. So differentiation of that Ke is going to result in what? Work function is a constant. So it's 0 minus hc and 1 by lambda differentiation will be minus 1 by lambda square into d lambda. So the small change in the kinetic energy is going to be hc by lambda square into d lambda. This is going to be helping you. Then next is what? You differentiate here. Lambda d, I'll write it as h by root 2m and I'll write it as Ke to the power minus 1 by 2. Now d times, that is differentiation of lambda d, is going to be h by root 2m is a constant, and differentiation of this minus half ke to the power minus 3 by 2 into differentiation of the ke. So I will leave this portion to you from now on. You know the differentiation of ke. Take this and keep it over here. Take this and keep it over here. And then you get the answer. Then you will definitely get the answer. See, they are talking about proportionality only. They are talking about proportionality only. It's not a big deal. You'll easily get the answer. Okay. With this, we are completely done with dual nature and matter. Next class, that is tomorrow, you will have one more which is going to be from 5 to 8. I'll complete the whole atoms. If possible, I'll try to club nuclei, but I think atoms itself is going to be taking around 3 hours if I am going to dig deep and start doing stuff. Let me find out. If I can squeeze in nuclei, I'll squeeze in nuclei also. Keep working hard, man. Keep working hard. All the best. Bye. All the best. Bye.